we can evaluate limits using a table of values. The general statement for a limit is given right here on the screen. I want to give a little side note. I want to apologize. It was pointed out to me that in my last couple of videos, my little laser pointer function wasn't working. So some of you couldn't actually see what it was I was gesturing at. But from here on out, that function will be working. So the general statement for a limit, for some function f of x, where x is approaching some value a, is shown here on the screen, and we usually denote this limiting value, the thing that our function is approaching, the behavior of our function in that region, as L. So this is the general limit. Now this is nice because using this concept that we talked about before, we said that we're interested when we're computing limits or we're evaluating limits, we're interested in seeing the behavior of the function as we approach from the left and as we approach from the right. And we want to see the behavior of that function. And this is nice because not all functions that we're interested in finding their limit for are evaluated at that specific place. We talked about that in the last video. Some functions have domain issues, but we're still interested in finding the behavior of the function in that region. So if we set up a table like this general table, what I'm going to do is I'm going to take my value that I'm approaching and I'm going to subtract some values from it. This part of the table represents approaching the value a from the left. And as we approach a from the left, what we can do with our function outputs on this part of the table is look for trends. Likewise, if I take my a value and I add some values to it, this part of the table represents approaching that value a from the right. And likewise, what we can do with our outputs of our function on this side of the table is we can look for trends. And what this will do is it will give us a good idea of how our function is behaving in the region of a, in the vicinity of a, even if the function is not defined at a. So let's look at some specific examples. So we're interested in evaluating this limit. The limit as x approaches 2 of this function. I have a drawing of this function on the screen. And from the last couple of lectures, you can kind of tell by looking at this graph what the limit of this function is. We can see that as we approach from the left and as we approach from the right, what we're actually approaching. So I've gone ahead and taken the liberty of replacing our a values in our table with 2, which is the value that we're interested in finding the limit or finding the behavior of the function in that vicinity. I've replaced our a values with 2 because that's our a in our limit. And once I find all these values, notice that I need to evaluate my function at those values. So I'll go ahead and replace everything in the table so we can see what's actually happening. So once again, these values represent approaching 2 from the left. And once we have those values filled in and we evaluate our function at those values, like I said, even though our function is not defined at the in the area or at the exact point where we're interested in taking the limit of, we can see a trend right here with these function values. And likewise, if I hop over that value and I look at some values from the right, I can also see a clear trend in the output of the function. On that side. So if I look at these values, it looks like as I approach from the left, I get a 3.9, 3.99, 3.99. It looks like we're tending toward 4 as we approach from the left. And likewise, as I approach from the right, I get 2.1, 2.01, 2.001. It looks like these numbers are getting closer and closer to 4. So I can say from this table that the limit of this function as x approaches 2 is equal to 4. And we can see that if we look at the graph. As I get closer and closer to 2, this limiting value gets closer and closer to 4. Let's look at another function. This is going to be a very popular and familiar function for us by the time we get done with this class because it's pretty fun to analyze and we can get a lot out of it. We can get a lot of theory out of it. So again, we're going to approach this limiting value. We're interested in the limit as x goes to 0 of sine of x over x. And we are undefined at 0, so we can't actually plug 0 into this function because we'd be dividing by 0. But if we look at the graph, we can see that we're clearly approaching some value as we approach from the left and the right. So again, we're going to approach from the left, and we're going to approach from the right using this table of values and see what we get. So let me replace all of these values in our table. So once again, this part of the table represents approaching from the left, and this part of the table represents approaching from the right. And if we look at our outputs of our functions, and all we need really is some technology to evaluate the function at these values. If we look at the outputs of the function on this side of the table, we can see a clear trend. If we look at the outputs of the value on this side of the table, we can see the same trend. So all these values as we approach 0, even though 0 is undefined, we cannot define our function at 0. All of these values seem to be approaching 1. We're getting closer and closer and closer to 1 the closer we get to our value 0. And as we approach from the right, we have some symmetry right here. This function is symmetric about the y-axis. So we get the same values. As I approach from the right, I get closer and closer and closer to 1. So we can go ahead and say that if we evaluate this limit, the limit as x approaches 0 of sine of x over x is equal to 1. Let's go ahead and do another example. Now, one of the things that's very nice about this method is that I actually don't need a visualization of the graph for this. So we're going to go ahead and use this method to evaluate this table, or evaluate this limit of this function. The limit as x goes to 4. Square root x minus 2 divided by the quantity x minus 4. I don't need to actually see what this function looks like. I can see how the function is behaving just by looking at the outputs in my table. One more time. The values in this part of the table represent approaching from the left, and the values in this part of the table represent approaching from right. And as we look at these inputs and study the outputs of the function, we're going to look for trends on this side of the table, the outputs of the function. See if we notice anything. So I'll go ahead and replace the values in this table with the actual function inputs and function outputs so we can see if we notice anything interesting happening. So these are the inputs and outputs to this function that I'm interested in. Again, I'm interested in examining the behavior of this function as x approaches 4. So if I look at this part of the table, my values are getting closer and closer to 4 from the left at 3.9, 3.99, 3.999. 4, the function is undefined as usual. I can't actually plug 4 into this function because I'll have a 0 in the denominator. That's a problem. We can't have that. And on this side of the table, I'm approaching from the left. Approaching from the right, I have numbers to the right of 4, which is 4.1, 4.01, 4.001. So we're approaching 4 from the right side. We're getting closer and closer to 4 from the right side. Now, if I examine the outputs in this part of my table, as I approach from the left, I have numbers, and I can see a trend. I can see this 0.25 kind of stays the same in all of these values. This one is the furthest away from 0.25. So 0.25158234, and then as I get closer, 3.99, I get 0.25015645, and then as I get 3.99, I get 0.25001563. So you can see a clear trend. It looks like as I approach from the left, I'm approaching 0.25. Now you might question that a little bit, and that's okay. You can go ahead and question these things. I encourage you to question these things and be curious, be interested. about what's actually happening. So let's see what happens as we approach from the right. I have values getting closer and closer to 4 from the right. So I have 4.1, 4.01, 4.001. Now I don't have quite as clear of a trend as I have over here. I have 0.25 over here and I have 0.24 over here. But so it's important for me to actually question what's happening. If I start furthest away, I get 0.2484. So I have this 0.24 in common all the time. So I'm going to look at the numbers to the right of that, those two decimals, and see what's actually happening. I have a 8.4 here, I have a 9.8 here, and then I have a 9.9 here. So these values, our 0.24 is the same. We're actually getting closer and closer to 0.25. So I have this trend as well. And if you're ever not sure, you can go ahead, and I encourage you to do this, add more values to the table. So if you're ever not sure, well, what happens if I put in 4.0001 or 4.00001? That will give you some more values and some more data to look at on this side. And you'll probably see that these decimals are disappearing, and I have just a bunch of 9s right here getting closer and closer to 0.25. Likewise, on this side of the table, I can add more values approaching from the left. What if I put in 3.9999 into this table, or 3.9999999? I'm pretty sure what would happen is that we're going to lose more and more of these values, and we're going to have zeros here, and we're going to keep this 0.25. So we can pretty safely say, even though we don't know what this function even looks like, we can pretty safely say that if I examine these trends, that the limit as x approaches 4 of this function is 0.25. That's all I have for you this lecture. I look forward to seeing you all very soon.